Imagine an endless list of numbers. At first, they jump wildly across the number line, but as you move further down the list, the jumps get smaller. The values zero in, locking onto a single, precise target. That behavior is a convergent sequence. It is the raw material used to build every major concept in calculus. Once you define how limits behave, you can construct continuity. From continuity, you derive derivatives, and from there, integrals. But if our definition of convergence is vague, that entire logical pipeline collapses. We need a rigorous mathematical way to prove when and how a sequence hits its target. Walter Rudin formalized this in Principles of Mathematical Analysis. Definition 3.1 states that a sequence converges if for every epsilon greater than 0, there is an integer n. Think of epsilon as a challenge, an arbitrary margin of error drawn above and below our target limit. The integer n is the response, a threshold on the timeline. After crossing n, every subsequent point in the sequence must permanently land inside the epsilon band. It works like a game. No matter how aggressively you shrink the epsilon band, you must always be able to find a threshold n that permanently traps the infinite remainder of the sequence. Rudin immediately pressure tests this definition with 5 distinct examples. Let's look at how they behave. This chart plots the sequence 1 over n. It produces an infinite number of unique values, but they are entirely contained between 0 and 1. As n grows, the values glide smoothly down, converging perfectly to 0. Sequence n squared goes the other way. The values grow larger with every step. There is no upper limit, which means no epsilon band could ever contain them. It diverges. Convergence doesn't require a smooth approach. In this alternating sequence, the values bounce above and below the target of 1. Because the distance of the bounces shrinks with each step, it ultimately gets trapped by the target band. A sequence can even be a static number. An infinite list consisting purely of ones has a range of exactly 1 value. It converges to 1 immediately. Now consider Rudin's 4th example, the sequence I to the power of n. Does an infinite sequence of imaginary numbers converge or diverge? Here is the complex plane plotting that sequence. The values cycle endlessly between I, -1, -I, and 1. The entire sequence is strictly bounded within the unit circle. But if you draw an epsilon bubble around I, the sequence jumps in and then immediately jumps back out. It never settles, so it diverges. Boundedness is a necessary requirement for convergence, but as the imaginary sequence shows, simply being bounded does not guarantee convergence. These observations form the basis of theorem 3.2. A sequence can only converge to one unique point, and every convergent sequence is bounded. This visualizes the logic. If you have 2 different targets, you can draw small enough epsilon bubbles around them so that they don't overlap. A sequence cannot permanently stay inside 2 separate bubbles at the same time. Once established, convergent limits follow the standard rules of arithmetic. Theorem 3.3 proves you can add, multiply, and divide sequences, and their limit points will compute the exact same way. Chapter 3 gives us 4 governing rules. Limits are fixed targets. Convergent sequences are bounded. Third, bounded sequences are not automatically convergent. And fourth, limits obey standard arithmetic. Understanding this threshold sets the exact terms for everything to come in mathematical analysis. In the next lesson, we will explore Cauchy sequences to see what happens when sequences converge without a clear target.